In this video, we will be going over quadratic functions and their graphs. So we have already learned different methods for solving quadratic equations, and in this section, we will learn how to graph quadratic functions. So let's begin with the definition of a quadratic function. A quadratic function is a function that can be written in the form f of x equals ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. We can also use y in place of f of x if we wish. So an example is f of x equals x squared plus 6x plus 10, which can also be written as y equals x squared plus 6x plus 10. And the domain for quadratic functions is the set of all real numbers, or from negative infinity to positive infinity. So let's begin with graphing f of x equals x squared, which is the same as y equals x squared. We can plot this by creating a table of ordered pairs. So let's plug in both positive and negative values for x. And now we can graph these points. The graph will be a smooth curve through these points, and we call this curve a parabola. The lowest point on a parabola opening upwards is called the vertex, which for this graph is 0, 0. If it was opening downwards, then it would be the highest point. Also, if we were to draw a line along the y-axis, we would get a mirror image along the line. Therefore, we say that the graph is symmetric about the y-axis, or the vertical line, x equals 0, and we call this line the axis of symmetry. And notice that the parabola opens upward. This happens when the coefficient of the quadratic term, x squared, is positive. If it is negative, it will actually open downwards. So quadratic equations can be written in the following forms. The first form being in vertex form, and we'll see why it's called that in a moment, and the second form being in standard form. And here is an example of the same equation written in the two different forms. You can check to see that they are equivalent equations. Okay, so let's go over the steps on how to graph quadratic equations written in vertex form. So if we have a quadratic function written in the following form, the vertex of the parabola is hk. The axis of symmetry will be the vertical line with equation x equals h. If a is positive, the parabola opens upward, and if a is negative, the parabola opens downward. And then you want to find another point or points that exist on the graph. So these steps will help guide us on how to graph the parabola and what it will look like. We also call this form vertex form since the vertex can be easily identified within the equation when it is written this way. Okay, so let's do an example of graphing a quadratic equation written in vertex form. So for this equation, since it is written in vertex form, it will be helpful to write down the information that we can gather from the equation. So the vertex will be hk. However, we want to be careful with the signs of h and k. In order to get it written in vertex form, we can rewrite the equation in the following way, with the subtraction inside the parentheses and the addition on the outside if it helps. Therefore, our values for h and k are -1 and -4, which will be our vertex. So a trick we can use for immediately identifying the vertex is that h will be the opposite of this term, and k will be the same as this term. So we can start with plotting the vertex, and then the axis of symmetry will have the equation x equals h or x equals -1. And we can draw this as a dotted line. This will just be as a guide since it is technically not part of the parabola. Also, we know that the parabola will open upward since a is positive. Now we can just choose a couple of points for x to the left or right of the vertex so that we can plot more points. We can start with plugging in 0 for x, which will then give us the point 0, -2. And since we know this graph is symmetrical about the line x equals -1, we can find the symmetrical counterpart, which is -2, -2. We can also plug in 1 for x, which will then give us the point 1, 4, and the symmetrical counterpart of this point is -3, 4. Now we have enough points to graph the parabola, and we can draw a smooth curve going through these points. And this will be the graph for the quadratic equation. So we may also have to graph equations that are written in standard form as opposed to vertex form. So let's write down the procedure for how we can graph a quadratic function written in standard form. There are two methods that we can use to graph quadratic equations written in standard form. The first method being that we can rewrite the equation written in standard form in vertex form by completing the square. And the second method would be to use the formula x equals negative b over 2a to find the x-coordinate of the vertex. Then the vertex will have the coordinates negative b over 2a, f of negative b over 2a. This notation just means that we plug in the x-coordinate of the vertex back into the equation in order to get the y-coordinate of the vertex. Also, if a is positive, the parabola opens upward, and if a is negative, the parabola opens downward. Let's begin with how we graph quadratic functions written in standard form using method 1. So for this example, first notice that the equation is written in standard form. So some information that we can get just by looking at the equation is that the parabola will open upwards since the coefficient of x squared is positive. So for method 1, we want to write this equation into vertex form. So we're going to want to complete the square on these terms. Let's move the constant to the other side of the equation by subtracting 10 from both sides. And now to complete the square for the right side, we will add 6 over 2 quantity squared, which is 9, to both sides of the equation. In doing so, now we have a perfect square trinomial. We can factor this as x plus 3 times x plus 3, which is the same as x plus 3 quantity squared. Then the last step to get it into vertex form is to solve for f of x, so we want to bring the constant to the right side by adding 1 to both sides. And now our equation is written in vertex form. We can easily identify the vertex. Again, it will be the opposite of this and the same as this, so our vertex is negative 3, 1. The axis of symmetry will be the line x equals h, which is x equals negative 3. So we can start with plotting the vertex and the axis of symmetry, and then we can create a table of ordered pairs so that we can find other points that exist on the parabola. So let's choose points near the vertex. We can start with x equals negative 2, and to find the y value, it does not matter which equation we use. So let's just use the vertex form equation. So we get the point negative 2, 2 as our first point, and the symmetrical counterpart will be negative 4, 2. And now let's try plugging in x equals negative 1, which will give us the point negative 1, 5, and the symmetrical counterpart will be negative 5, 5. Now we have enough points to sketch this out and get the basic shape of the parabola. So we draw a smooth curve going through these points. And we are done. We have written the equation in vertex form and have also graphed the function. For the next equation, again, this is written in standard form. So some information that we can get just by looking at the equation is that the parabola will open downwards since the coefficient of x squared is negative. So using method 1, we will want to write the equation in vertex form by completing the square on these terms. So let's first add 6 to both sides of the equation. And we also need the coefficient of x squared to be positive 1 first before we complete the square. So let's multiply both sides of the equation by negative 2 and simplify. And now that we have a coefficient of 1 for the x squared term, we can complete the square. So we're going to add negative 8 over 2 quantity squared, which is 16, to both sides of the equation. This will then give us a perfect square trinomial on this side, which will factor to x minus 4 times x minus 4, or simply x minus 4 quantity squared. And the last step into getting this into vertex form is to isolate g of x. So we subtract 4 from both sides of the equation, and then we divide both sides by negative 2 and simplify. This will then give us g of x equals -1/2 times x minus 4 quantity squared plus 2, which is now written in vertex form. We can easily identify the vertex, which will be the opposite of this term and the same as this term, so 4, 2. Our axis of symmetry will be the line x equals h, or x equals 4. And we could start with plotting the vertex and the axis of symmetry. And now we can create a table of ordered pairs in order to find some other points that exist on the parabola. We can start with x equals 2, which will give us the point 2, 0, and the symmetrical counterpart of this will be 6, 0. We can also plug in 0 for x, which will then give us the point 0, -6, and the symmetrical counterpart of this will be 8, -6. And now that we have enough points to graph the parabola, we can draw a smooth curve going through these points. And now we have finished graphing the parabola, and we have also written the equation in vertex form. Now let's go over how to graph quadratic functions using method 2. And as a reminder, method 2 will be using this vertex formula. So let's go over an example of how we can apply this formula to find our vertex. So for this example, since this equation is written in standard form, we can use method 2 and find the vertex first. Let's identify the values for a, b, and c. So a is equal to 1, b is equal to -6, and c is equal to 3. So the x-coordinate of our vertex is given by -b over 2a, so we have -6 over 2 times 1, which will simplify to +3. So the x-coordinate of our vertex is 3, and we plug this value into our equation to find the y-coordinate of the vertex. This will give us -6 as the y-coordinate. Therefore, the vertex is 3, -6. And once we know the vertex, we also know the axis of symmetry, which is x equals 3. And we also know that the parabola will open upwards since the coefficient of the x squared term is positive. And now let's start by graphing the vertex and the axis of symmetry. And now we can create a table of ordered pairs to find other points that exist on the parabola. So plugging in 2 for x, we get the point 2, -5. And the symmetrical counterpart will be 4, -5. We can plug in 0 for x, and we get the point 0, 3. And the symmetrical counterpart to this will be 6, 3. And now we have enough points to graph our parabola, so we draw a smooth curve going through these points. And now we have finished graphing the function.